So good afternoon, everybody. It is a real pleasure for me to introduce the last speaker for today, Professor David Seidman. I've known David since the materials conference that was held here in 2009. I was fortunate to spend my sabbatical with him at Northwestern University. David is a member of the International Advisory Board of the Department of Material Science and Engineering at Tel Aviv University. He is the most active board member, and I'm taking advantage of his expertise, and he's really my secret advisor with many things related to the development of the department. So I'm very happy. And he was also the driving force behind the initiation of this collaboration between the department at Northwestern and the department here. And in general, he's the leader there, I should say, or the driving force with all of the interactions with Israel in general. He's a warm supporter of Israel, real Zionist. So with this, it is a great pleasure for me to invite him. The talk will be a review of the atom probe tomography, a field in which David is considered as one of the leaders worldwide. So David, welcome.
Okay, thank you.
Be careful.
I have to be careful now. Noam, do you have one of these Logitech devices?
Yes, I do.
Oh, here. Oh, thanks a lot. Yeah. Okay. Oh, yeah. Oh, yeah, it's on, but it's red, the light. The light is red, but it's on.
Okay. You have the right one.
I have the, okay. Okay. Okay, thank you for coming. Last talk of the day. So what I'm going to do in this talk, I'm going to have a kind of an overview of atom probe tomography as a technique, and it'll be longer than the one that I gave on Sunday, so there will be some additional slides there. And I thought I would try and give you the basics. Unlike Peter Voorhees, where he very systematically went through the whole basic theory of phase field modeling, what I'm going to do is to give some examples that explain the technique. And only part of it is published. The first thing I want to talk about is nano diamonds. We've been looking at nano diamonds, which has turned out to be very challenging for reasons that I'll explain. And then I'll talk to you about silicon nanowires that involves a cooperation between Yossi Rosenbachs and Roy Yerushalmi at the Hebrew University, and also some work with a fellow in Montreal who I've been interacting with for a number of years. Okay, so what is an atom probe? What is an atom probe tomograph? It's basically a combination of two techniques. One is field ion microscopy, where you see atoms in direct space, and a special time of flight mass spectrometer. And I'm going to give you a short tutorial. Okay. So here is field ion microscopy, kind of in a nutshell. Okay, so I'll just go back. This is a wire, a specimen, sharply pointed, with a nano radius, and now this is a simulation of a field ion microscope tip, and the atoms, each spot corresponds to an atom, and the atoms that are in red are the ones that you see in a real image. And if you look at a very close packed plane like this plane, okay, I can't catch it. Okay, so, but it'll reappear. Okay, yeah. So if you look at a close packed plane, you can see almost all the atoms. Not quite, but you can see, and I'll show you real examples. And on this plane, you see 5 atoms. And that occurs also with the actual technique. This also is a model. In this model, these are small balls, and the ones that are painted white, those are the ones that you see. This is an FCC structure, and it's a 1, 0, 0 axis. So this image has fourfold symmetry to it. Okay, this is a real image of tungsten, a very sharply pointed tip, and it's a 110 plane here, and it has twofold symmetry. And if you look on a small plane, this plane over here, you see each individual atom. Okay, how do you image these atoms? What is the messenger that carries these atoms such that you can see them? So this is the simulation, once again. And field ion microscopy was invented by the late Erwin Mueller and his PhD student, Bahadur. And it was 11th of October, 1955. So it's it'll be 60 years old this year. And it was the first observation in direct lattice space, okay? And how do you see it? What's done is to put a tip at a high positive potential with respect to Earth to generate very high electric fields. And in Feynman's book, the one volume on electricity and magnetism, he talks about this instrument, but he calls it a field emission microscope, which is not right, but he talks about it as a way of generating very high electric fields. So the imaging, what carries an image to your eyes are helium atoms. So you bleed in a small partial pressure, maybe 10 to the minus 4, 10 to the minus 5 torr of helium gas into an ultra-high vacuum system. Well, the original instrument was not UHV. And these helium atoms are polarized in the high electric fields. For tungsten, which has a very high evaporation field, I'll explain that term to you in a minute, you need a field, well, you need a field of about 4.5 volts per angstrom to ionize a helium atom. But it's polarized, so it comes in with a very high effective temperature, and it hits the surface, and it becomes accommodated in a few hops on the surface to the temperature of the tip, which is at cryogenic temperatures. And so its velocity is then very slow. Its velocity is very slow, and it's ionized in a region that's above each atom, and in that region, the atom becomes positively charged. And once it becomes positively charged, it's repelled from the tip. Now, you have originally it was just a phosphor screen here. Now we have these high gain detector plates, and so you have a cone of ions. You have a cone of helium ions, and each time the helium ion hits the phosphor originally, it gives off light. The total current from the tip is maybe 10 to the minus 8, 10 to the minus 9 amps. So the actual current from an individual atom that, is very tiny, but it's enough to see the image. It's enough to see an image of an atom. And also the fact that it's accommodated to the temperature of the tip means that the transverse velocity is small. So the spots can be extremely small when you cool the temperature, say, which we've done, to 10 degrees Kelvin or so. So you get these beautiful patterns with symmetry, and to first order, what you see on the screen is a stereographic projection. Okay, so there are the elements here. You need a high field to ionize the atoms, and Mueller discovered this, but he didn't understand. Well, he understood that, I think. The next thing, if you keep increasing the voltage, increasing the field, the atoms begin to field evaporate. They sublime. They basically sublime. You can sublime atoms at, to whatever temperature you go to, 10 degrees Kelvin. If you can get it to 4.2, you're subliming atoms at 4.2 degrees, okay? And so there are two quantities here. One is the field to ionize, and one is the field to evaporate the atoms. Okay, nowadays, and I'll explain this to you in a moment, with the arrival of atom probe tomographs or atom probe tomographs, the problem is people have stopped taking field ion images, but there's a lot of information in them, and part of the problem is technical, just the way these instruments are built. With Christina Stiller, who's in Gothenburg in Sweden, I wrote a short primer with her explaining the technique, and it's in a special issue of the MRS Bulletin. Okay. Now with our present instrument, rather than using voltage pulses, originally people used voltage pulses to evaporate the atoms from the surface of the tip. Now we use a UHV laser, and it's a picosecond laser, and it has a wavelength of about 355 nanometers. And this turns out to be a game changer for this whole technique. And the energies per pulse are of the order of picojoules. You can go down to picojoules. Before this, we had a green laser, and we were using nanojoules. Okay, this is the issue I mentioned to you. And these are the kind of things, there are several articles in here. I forget how many, maybe 5 articles, covering all different materials classes, even soft materials. And you can measure things like dopant distributions in 3 dimensions. You can measure interfacial roughness. I won't talk too much about this. You can look at the distribution of elements laterally and in depth, as I'll show you. You can look at segregation at defect sites, for example, interfaces. You can look at evolutions of phases. You can see first-order phase transformations, which we've studied a lot. And, and these revolve around kinetics and diffusion issues. All these things you can do with the instrument on a certain length scale. Okay. Now, the most common instrument now is a commercial instrument that we've had since December 2004, and it's called the Local Electrode Atom Probe, LEAP, and it was it's a good name because it is a leap forward. The people who thought it up were quite good. And the generic name is atom probe tomography because it is a 3-dimensional technique. It is a tomograph. So it's really unique for determining chemical compositions on a nanoscale, and you can do this in 3 dimensions. You can reconstruct the lattice in 3 dimensions. You don't get a perfect reconstruction like a ball and stick model that you can buy to teach your students crystallography, but for many things it's good enough. And I just want to emphasize it involves a combination of both field ion microscopy, where you can see atoms in direct space, plus this special time of flight mass spectrometer, and it has single ion sensitivity. It means you can detect 1 ion at a time, and that's because the primary detector has a gain of 10 to the 7th, with low noise. Okay, so you can reconstruct in 3 dimensions, in real space, direct space, and you get the mass-to-charge state ratio essentially from conservation of energy. Mass-to-charge, charge on an electron, the effective voltage. When you use a laser, this is an effective voltage, so it's the voltage, the DC voltage that sits on the specimen plus the voltage due to the laser, and that's what I mean, it's an effective voltage. And T is the time of flight, and D is the flight path, and you can calibrate D using the known isotopes of a specimen. Something like tungsten that has 5 isotopes, or molybdenum that has 7 isotopes, and using also helium, and it's linear from hydrogen to the top of the periodic table. Okay, and the depth resolution is equal to the interplanar spacing between different HKL planes, and that can be less than 1/10 of a nanometer. The lateral resolution is 0.2 to 0.4 nanometers for a given crystallographic plane. The present detector efficiency is between 50 and 60%, and that's determined by the open area of the channel plate. There are now channel plates available that have open areas of up to 80% commercially. Okay, so this means that all the elements in the periodic table are detected with equal efficiency once the energy of the evaporating ion is above a few kilovolts. Channel plates have been around for a long time. They're well over 50 years old, and they were developed in the United States. I think it was in an Army research lab for night vision to replace sniper scopes that were used in World War II. So when you see soldiers, when you see soldiers in the dark shooting, the image is usually in green, and that green is from the phosphor that they use. So these channel plates, this is what makes the technique possible. One of the things that makes the technique possible. This is from the manufacturers of the instrument, and this is a photograph that we took ourselves. and now you can't see anything of the instrument. Once they put the laser light on, it's all a lot of black boxes because it meets OSHA 1A standards, okay? And you don't have to wear special glasses or anything around the laser. Okay, so these are some of the characteristics of what we have in the instrument. We can examine greater than about 10 to the 6 cubic nanometers. The largest viewing area is about 200 by 200 square nanometers. And we have an ultra-high vacuum. We can get down to 2 times 10 to the minus 11 torr. We rarely break vacuum. The only time we break vacuum is when the instrument has a semi-annual checkup, which comes with the service contract. The specimen temperature, we can vary it from room temperature down to about 20 degrees Kelvin. And this over here is a closed cycle refrigerator. And we have a chamber here that can hold up to, it has 4 levels. It has 4 levels, and per level it's 6 specimens, so 24 specimens. So we minimize opening things to the air. With electrical pulses, we can go up to about 500 kilohertz, and with a laser, we rarely do it. We can go up to 1,000 kilohertz. You need a high repetition rate because you don't want the detection efficiency to be too high. If the detection efficiency is too high, you have problems with pileup, et cetera. And so we want a detection efficiency that's about 1%. And with a detection efficiency of, say, 1%, you need to pulse very fast such that you can collect the data set in a reasonable amount of time. Okay, so here is an example of how it. So here is a multi-layer of red atoms and blue atoms with some green impurity atoms. And this basically is what you see on the monitor during the course of an experiment. And this curvature is due to a geometric effect. This distance between the nanotip and the detector here is about 80 millimeters. It's a very short flight path. And then you reconstruct. Basically, you level the planes out. And this is what you see on the monitor. And when you transfer the data set to a workstation, you can rotate the data set almost, you can rotate it continuously, okay? Now here is the model, a cartoon of how the instrument works. This is the local electrode. This is your detector, primary detector, which consists of a channel plate, and then these lines here at 90 degrees to one another, they're a so-called delay line detector. So from the time of flight to the channel plate, you get the mass-to-charge state ratio. And where the cloud of electrons that comes out the backside of the channel plate hits these lines, from that you get the precision of the atom on this tip. So say this is a silicon nanowire. Here's a little bit of gold. It was grown by the so-called vapor-liquid-solid technique. You bring this quite close. This orifice, this opening, is of the order of maybe 40 microns or so, and you want to bring it to within 40 microns because that enhances the electrical field, and you don't have to use such large voltages, high voltages. Okay, so here is the tip. It's at a positive potential with respect to Earth. And as I said before, using the laser light or voltage pulses, you can evaporate atoms. You can physically evaporate atoms from the surface. And the reason for this is, in the presence of these high electric fields, you bend the interatomic potential into a curve that looks like this, and this is the so-called Schottky hump. Okay, and then the next step is you hit it with a laser light, and then this guy comes off the surface. It goes over the Schottky hump, and then it goes and hits your detector, but it's positively charged. And this is a highly controllable process, and you have a clock, an electronic clock, so to speak, and the clock runs, and you then plot the number of counts for a given mass-to-charge state ratio, and this gives you then a mass spectrum. This is your mass spectrum over here. Okay, now here's an example. Here's a simple example, but it's an important one. So this is for a silicon boron alloy, so to speak. and you'll notice several things. This is counts per channel, mass to charge state ratio. Number one, let's look at the bottom end. Here you have boron in a doubly charged state, boron 10, boron 11 in a doubly charged state. Here you have the same species, boron, but in a singly charged state. And you can try and predict these states with a model which predicts that you should mainly get doubly charged ions, but you get other charged states. And now here is the silicon. Here are the three isotopes of silicon, 28, 29, 30, in the doubly charged state. And one of the things that you can do, which is a form of a test of the instrument, you simply count the number of events under each of these peaks, and then you look in a handbook and you see what the isotopic abundances are. So if you get the correct isotopic abundances, then you know you're doing something right, okay? There are no problems. The other thing you should notice here, this is only 10 counts. This is the white noise in the system, and that's a very quiet system. It's not very noisy. And what this means is that you can measure small concentrations. We've measured, in a few cases, as small as 7 atomic parts per million. Okay. It's simply a counting technique. You want the data set to be as big as possible so you have as many counts as possible. Okay, I think those are the main points about this mass spectrum. And if you look at the mass resolving power, M over delta M, say for aluminum, which is 27 in the singly charged state, then the full width at 10th maximum is 1,000, and I'm sorry, the full width at 10th maximum is 500, and the full width at half maximum is about 1,000. So you can get very sharp peaks. You can get very sharp peaks. And the other point, I'll just remake this point, it's important, if you have good statistics, a lot of data, then you can count to at least 10 atomic parts per million. So if you have a data set of 1 million atoms, right, 10 to the 6th, it means you will find one atom. But you can get data sets. We've gotten data sets. It depends on the material. We can get data sets as big as 500 million atoms, 600 million. It doesn't seem like a lot, but it is a lot, and there's a lot of information there. Okay, let's look at another example. This is a comparison of the LEAP with SIMS, basically. So here is the atomic concentration, and it's a CVD-grown silicon germanium alloy. The germanium has a concentration of 6%. And this is depth into the specimen. And the continuous purple curve, that's from the SIMS, scanning ion mass spectrometry, which is widely used. And you can see with the data in blue, okay, there's noise in it, of course, because the signal is smaller than in SIMS, but you'll notice how quickly the signal drops as you hit the interface. Whereas in the case of the SIMS, you notice how broad the interface is. So for LEAP, in 1 nanometer, it drops a decade, whereas it takes 7 nanometers per decade for the SIMS. Okay. This came from Kamika. We didn't do this. Okay. The other thing which is quite important is very often you're dealing with a system, say precipitates, a second phase, where you have a lot of them. You have many of them. And you don't want to have to go and analyze them one by hand. So we developed a technique with a postdoc, Olaf Hellman, who now works for Microsoft for many years, this so-called proximity histogram, and it's a 3D nonlinear composition profile. So let's say there are 2 species in your system. Let's say there are yellow atoms and orange atoms, and we want to find the interface between the 2 phases. How do we do that? Well, what we do is, let's say that we're dealing with a sphere. You put a shell around that sphere, an annular shell with a certain thickness, and then another shell around it, etc. And in each one of these shells, you measure the concentration in 3D. And when you do that, you get a point. For each shell, you get a point, okay? And there's a trade-off here. you want the concentration in each cell to have a small error bar associated with it, but that's a problem because that's hard. So there's a trade-off between the thickness of the shell and how accurate the measurements are. So you generate these two curves, okay, for the orange atoms and the yellow atoms, and then you have to pick an interface. And we typically pick an interface at the inflection point of the majority species. You have 2 species in a system, 3, 4, 5, whatever. We pick the interface by definition to be at the inflection point of that. And this is really 3-dimensional information which has been compressed into 2 dimensions. The other point about it, it's independent of the convexity of the surface. So you could have a surface that is both concave and convex, and you can use this approach. And it works very nicely for giving you average concentrations. And so over here, I simply say it's invariant to the interfacial geometry. Now, what we've been doing for many years, and we called it simply combined. We combined TEM with atom probe tomography, and now the buzzword is correlative, that you make a correlation between the 2 sets of results, TEM and APT analysis. And here's an example. It involves, she was then at UC Davis, Ilka Arslan. And, she was my former PhD student, Emmanuel Marquis. She was working at Sandia Livermore. And what they did is they combined 2 techniques, the atom probe technique with high-resolution electron microscopy, well, doing not really high resolution, doing tomographic microscopy, and they had a spatial resolution of about 10 nanometers at that time. And this is for the system aluminum-silver, so these are aluminum-silver precipitates, and where they, on the same specimen, and where you only see 1 color, it means they overlap, and where you see 2 colors, it means that they're not overlapping exactly in 3-dimensional space. And there's a table here. There is a table here of the advantages of TEM versus atom probe tomography. And over here, this is the good points, the weak points. And I'm not going to go through this table with you in detail, but they both have their pluses and minuses, so to speak. But you can make good correlations between TEM and APT results. Okay. The final line down here is quite important. You have to use, in many cases, a dual beam fib to make specimens. You have no choice, as I'll show you. And if you can't electropolish a specimen, then you have to use the dual beam fib. You have to. If say you're interested in something in depth like this, multi-layer, you have to, as I'll show you, use the dual beam fib to make the specimen. So a critical part of this, just like in electron microscopy, but it maybe even more so, is using the dual beam fib. Okay. Now I want to show you, this is something that, a problem that was really brought to me. I was contacted by 2 different groups. One group from University of Washington in St. Louis, so-called WashU, and that's its nickname, WashU. And the other group was at the University of Chicago and Oregon, and they call themselves cosmochemists. I had never heard the term cosmochemist before, but they are cosmochemists. And what they're very interested in knowing about is the ratio of isotopes of carbon. And in particular, there is a famous it wasn't famous until they told me it was famous, a famous meteorite that is older than the age of our solar system. It's in excess of 4.5 billion years. And they said, we have nanodiamonds from this, from this meteorite. And the first question I asked them, how many do you have? And they said, don't worry. We have all that you'll ever want. Okay, and the reason is, what they do is they dissolve the meteorite, and what's left are nanodiamonds and nanoparticles of silicon carbide. And what they're interested in is the ratio of 2 carbon isotopes, carbon-12 to carbon-13. Okay, and because that will tell them something about what the universe was like before our solar system was created. It's a problem they were both working on. at the time. And the guy who first came to me, he passed away, unfortunately, is Frank Steidman, and his wife is Christine Floss, and she's continuing on, and Joe Ben Lewis is their PhD student. And Dieter Isheim is a research associate professor who's worked with me probably maybe 16, 17 years now. Okay, so the first challenge, and it was non-trivial, was to make specimens given these nanodiamonds, okay? And we weren't sure whether we could do it, and we told them, you know, it's not going to be easy. And they said, don't worry, it's important to us. There are supposedly 900 cosmochemists in the world. So when they have a meeting, 900 of them plus their students attend. So look at panel A here. This is a nickel substrate, okay? So what we do is to deposit platinum using an ion beam sputtering system made by South Bend. We sputter a layer of platinum, and then we put in nanodiamonds here. You see in black the nanodiamonds. We put another layer of platinum on top of it using this so-called IBS, and then we put a buffer layer on top of that. Okay, go to B. I'll show you how we get to B. We have over here, you see this well, this is a triangle cross-section, and here is this layer containing the nanodiamonds, and we put it, this is a silicon microtip, and this is a piece of platinum over here, and we weld this, essentially cold weld this triangular shaped piece, which has a thickness to it, to this platinum patch. Okay? And so here, the next step is to make a tip out of it, a nanotip out of it, and that's where we use the dual beam fib, and you see we also put a protective layer on platinum here. And then we use the so-called fib, and we use gallium ion beams to sputter the material to have this shape. And here is the final product, you know, and these black atoms, these regions of black atoms are the nanodiamonds, and they have a mean diameter of about 3 nanometers, and they contain about 2,500 atoms, of which we can only detect about 50%. And the big problem is counting the carbon-13 atoms. That's the biggest problem. Okay? So here you see what's done. The first step is that you have the nanodiamonds in a water suspension, and you put a droplet of it on the surface. And you notice a lot of them go to the periphery of the droplet. And then we use ion beam sputtering to put the layers on. And this is just a schematic of that also. And here is the nanodiamonds inside the platinum sandwich. And here's a blow-up, a schematic blow-up of it. Okay? So this is the end product. So you go from nickel, platinum, nanodiamonds, platinum, nickel. So we have this complicated sandwich here. Okay, now here's my layer of nanodiamonds. And once again, if you look in panel B here, you'll see a blow-up of it. If you follow these red lines across, you can see here, follow this red line, and here's the nanodiamonds in that sandwich. Okay. And then what we do in this step over here is we cut out a piece like this from this sandwich. This has a cross-section that's triangular shaped. And then that's step D. Look at the length scale here, 10 microns. And then in the dual beam fib, there's a micromanipulator, and you lift it out, and you attach it to this so-called arm or rotatable needle, such that you can wind up in this state here with the nanodiamonds along the axis of the specimen. And then using this pattern here, annular milling pattern, we wind up with this needle shape like a specimen. Once again, notice where the nanodiamonds are. Okay? And this is what we want to analyze. And you see, we've analyzed in this research that I'm going to tell you about less than 100 of these. And here, once again, this is the atom probe, and it points to where these clusters, or they call them clusters, we call them nanodiamonds. They're clusters of carbon atoms. And this appeared in a journal that I never heard of until I met these guys, Meteoritics and Planetary Science. Okay. Now here's what the mass spectrum looks like. And you see, you focus on the carbon atoms, carbon-12, as well as carbon-13. And here they're in the doubly charged state. And here's carbon-12 in the singly charged state. And here's carbon-13 in the doubly charged state. And then you also have trimers of carbon atoms in the doubly charged state. You have dimers of carbon atoms in the singly charged state and a trimer in the singly charged state. And you can see the background. This is logarithmic scale, but it's relatively clean, the background. Now, if we extract from this the uncorrected isotopic ratios of carbon-12 to carbon-13, we get about 54 plus or minus 4. And then in the singly charged state, it's about 61 plus or minus 4. Okay. Now, in these nanodiamonds, that exists in nature about 0.5% nitrogen. There's some silicon present and some oxygen present also, as you can see from the mass spectra. Okay, so let me get to the bottom line here. Now, if you measure concentrations in atomic fractions of the two isotopes, carbon-12 is about 89%, and if you measure it in mole fraction, it's about 92. Okay, so these two panels, these are all terrestrial results, okay? One of them is made by detonating diamonds to get small nanodiamonds. So these are all synthetic nanodiamonds from left to right. And on the right-hand side, you have our measurements of the atom probe tomographic measurements. And the name of the diamond, by the way, is Allende. That's not the diamond. The name of the meteorite is Allende. And what we find is experimentally is that our ratio is less than the terrestrial ratio on the average. And there's other evidence for that. So here's a plot, and this plot is the ratio in the singly charged state of carbon-12 to carbon-13, and here it is in the doubly charged state. And in principle, they should be the same. This is a line at 45 degrees, but they're not. It tends to favor singly charged as opposed to doubly charged. Okay, so this is the same plot here of carbon-12 to carbon-13, singly charged, doubly charged. And these dashed lines, this dashed line, the vertical one and the horizontal line, you see this is about 89%. This is about 89% here. And those would be the terrestrial values. And there are two sets of data here plotted. One are our standards, and one is from the Allende meteorite. And so the one that's kind of small, this small spot here, is from the Allende meteorite, and the big spot is from our standards. And this is a summary of the results. So this you see from the terrestrial diamonds is about 67 plus or minus 4, and this is 69 plus or minus 3, and this is 2 sigma for I'm going to get it wrong. This is this is not the standard deviation, but it's this quantity sigma sub xm is a measure of the precision of the measurements. This sigma over here is the scatter of the specimen of the results, and ideally you want this sigma to be, which is the precision, to be very small. And we did it for the singly charged and the doubly charged, and there are differences. So the bottom line from all of this is that we see less than the terrestrial value. There are also astronomical results from a carbon star that also show the same result. We're not through analyzing the data. There are a lot of subtleties to analyzing this data. So what have we shown here? We've shown that nanometer-sized particles can be analyzed by this sandwiching technique, and we can measure local isotopic concentrations associated with the diamonds, and we're using synthetic nanodiamond particles that are terrestrial to use as a standard, and we want to see how close we come to the what we would expect to the terrestrial value. Is it above or below? And right now the situation is for 100 particles, we're below the terrestrial value. Okay? Okay, what are the next steps? We have to make some dead time corrections, it turns out, in this, because we only have a resolution of about 2 nanoseconds in our measurements, and we want to include we included APT data, atom probe tomographic data, from these bulk specimens, engineered nano diamonds, and our goal now is to reduce the scatter, to make the measurements more precise. We have to look at more nano diamonds. Okay. Now, I also mentioned there is a new LEAP 5000 with a detector that has an efficiency of between 75 and 80%, which means we'll see more carbon atoms, more carbon ions, which will improve particularly the statistics for carbon-13, because we only have about 2,500 total atoms per nanodiamond. Okay. We've been cooperating with a fellow named Usama Mutanabir, and I met him first through a friend of mine when he was doing a postdoc in Germany, and now he's an assistant professor in Montreal, and this is his graduate student, Samik Mukherjee. Okay, so what I'm going to, how much time do I have left? What? 20 minutes? Okay. Yeah, no, that's plenty. Okay, so when he was at this Max Planck Institute in Halle in Germany, they had developed techniques there for growing nanowires using aluminum as the catalyst rather than gold. You know, gold's a problem because it kills the minority lifetime, the minority carrier lifetime. 10 minutes. Okay, I'll just do this. Okay, why aluminum silicon? First of all, aluminum is very common in silicon materials, and it has, it has applications. One of them is to silicon photovoltaic cells, and also people have created aluminum P+ regions in the rear of N-type silicon cells. People also use aluminum doped with silicon to demonstrate fabrication of PN diodes and bipolar transistors. Okay, as I mentioned already, it replaces using gold. Okay, and they mastered this technique in Halle. Okay, so what did we find by analyzing the specimens? That's the question. So there were 2 species that we were interested in, actually 3 species. One is aluminum, one is silicon, and the other one is oxygen. So here is a 3D map. The aluminum is in red, the silicon's in blue. You're only seeing 1.8% of the silicon atoms. Otherwise, it would look like a blur. It would look like an absolute blur, and you would see nothing. Okay, and this volume of material, these are its dimensions, about 75 by 75 by 65 cubic nanometers. Okay, and this contains about almost 10 to the 6 times 10 to the 6th atoms, almost 10 to the 7th atoms. These are all the same data sets analyzed in different ways. So in B, what we're doing is we're using a 2 atomic percent aluminum isoconcentration surface. In other words, we define an isoconcentration surface, and we use those to define the precipitates. Okay, and now here is the same thing in C, and this is at just a different, we can turn it in different directions, and you see different things when you turn it in 3D. So here's just another view of that same data set, and here is a cross-sectional view, and in this case, it's not clear. They look along a line, but I'm not sure that just in this image, but I don't think that's absolutely true. Okay, what's the total aluminum concentration that we find in this data set? And these were processed at 600 degrees C, and it's about 1/10 of atomic percent aluminum. The other thing that we found is we found oxygen precipitates. And we define the oxygen precipitates in the same way that we define aluminum precipitates with an isoconcentration surface. And in this case, the isoconcentration surface is in this kind of greenish color. Okay, and now we superimpose the two sets of data. So this is a 2 atomic percent aluminum isoconcentration surface and a 1 atomic percent oxygen isoconcentration. You might be asking, how do we pick these numbers? It's by experience. This is where there's some art to the subject. To get the right to pick the right isoconcentration surface is important. Okay, now we make here a plot. This is the volume of the precipitates in cubic nanometers, and the O, well, the kind of O is oxygen, of course, and aluminum here is in red, oxygen is in kind of green, and this is the concentration in each of these precipitates. And this was the analysis here was done by hand. It's for 89 precipitates, and you see there was some precipitates as big as almost 100 cubic nanometers, and this line over here corresponds to about a mean concentration of about 2.2, and for the aluminum it corresponds to a mean concentration of about 5.3. And the other thing that we have plotted here is the volume of the precipitates versus the ratio of aluminum to oxygen, where these are measured in atomic fraction. And so you can see that the mean value here of this ratio is about 2. Twice as many aluminum atoms as there are oxygen atoms. Okay, and now the other thing we can do, we've developed software to do this ourselves, is to measure the edge-to-edge distance between these precipitates. So what is the mean edge-to-edge distance in 3 dimensions between these precipitates? How far are they from one another? And they're about 15 nanometers apart. And then what you can do with that information is you can create this distribution, which is the probability of finding a certain interprecipitate distance. And you see it has a maximum here at around somewhere, I'm looking at an angle here, this is somewhere around 11. We need more data points. I mean, we had 89 precipitates. This analysis part is not trivial. It's a lot of work. Okay, now let me show you the mass spectra. And I'm doing this because I want you to compare the entire mass spectrum, this is of everything we collect, versus the mass spectrum where you focus on the aluminum and oxygen-rich precipitates, and you can see the difference. You can quite easily see the difference between the two mass spectra. Okay. Now, the other piece of information we can get, and this is, once again, you have to do it for a single precipitate. This is done for one precipitate. So this is concentration versus distance. And this is, 0 here is the interface. I explained to you how we picked the interface. It's approximately the inflection point in each one of these concentration profiles. So you have 2 concentration profiles, one for aluminum and one for the silicon. And so you can see when you're away from the precipitate, essentially their concentrations are not exactly 0, obviously, but they're much smaller than when you go into the precipitate. All this noise here, the reason for noise in this is that when you go, it's a spherical precipitate, say approximately, and as you go toward the center of the precipitate, you have fewer and fewer atoms, so the data bars get bigger and bigger. There's no choice with that, no choice whatsoever. Okay, and then plotted in this inset figure here is the aluminum to oxygen ratio, and you can see it's essentially a constant approximately of about 2 as a function of distance. This is the interface, this is inside the precipitate, and this would be in the matrix away from the precipitate interface. Okay, the other thing that we did in some detail is to combine TEM here. This is a TEM image, and this is an atom probe image. And here is the silicon nanowire. Up here is the catalyst. This is the catalyst, and it should be pure aluminum, but it's not. And then the blue is silicon, remember that. and this is a diffraction pattern, and this is a high-resolution image of that interface. Here's aluminum, here's silicon. You can see the interface. So here's aluminum, here's silicon, and that's this interface between the aluminum silicon. And we put a cap on the specimen. It's pure nickel. So this surrounding cap is nickel. That was done intentionally, so we could analyze the specimen better. And here you see another TEM image of the silicon nanowire, and on top you see the catalyst, the aluminum. So what do you see here? You see aluminum is distributed inside the specimen as well as silicon. And if you look here at the cap, you also see nickel atoms present in that. Okay? Okay, now this is a single aluminum nanoparticle like this. And if you analyze this, this is the x direction and this is the z direction. And correspondingly, on this graph here, this is the x direction and this is concentration. So we can get two concentration profiles, one in the x and one in the z. This concentration profile is in the x direction. And this is of this nanoparticle, which is aluminum rich here. This is aluminum rich. And then you see the silicon here, down here, and it's silicon poor. So there's an admixture in this cap of aluminum and silicon atoms. And now you see here this three-dimensional distribution of aluminum atoms that's within the silicon nanowire. And the question is, these are individual silicon wires. The question is, are these randomly distributed? And we've developed a technique where you can calculate partial radial distribution functions and say how random. And it looks to first order like they're random. Okay, so what do we learn from this? That we can do atom-by-atom mapping of both semiconductors and dielectric materials on an atomic scale using UV laser dissection. The atom-by-atom dissection shows that the aluminum atoms precipitate in silicon matrix, and they form aluminum-rich regions with an average aluminum concentration of about 10 atomic percent. This is the range of diameters, 1.3 to 6.2, and these nanoscale precipitates also contain oxygen impurities, 4.4%, and so this gives us a very clear picture. And now you have to ask yourself, what is the aluminum solid solubility in silicon? And that's been measured at Bell Labs a long time ago, and it's much smaller. It's much smaller than, oh, okay, my time's up. This is the last slide, very good. It's much smaller than what we measure, so everything that we're seeing is a kinetic effect. It's not a thermodynamic effect. These are not equilibrium thermodynamic values, but these are kinetic values. So this is just a summary here, aluminum concentration versus distance. And you can see we're several orders of magnitude greater than the equilibrium solubility and 10 to 100 times the concentrations of solid solutions known in non-equilibrium processes. So these concentrations are extremely high. And it's for kinetic reasons, nothing to do with equilibrium thermodynamics. So I think I'll stop here at this point. Thank you.
Thank you, David, for this splendid talk. We have time for questions. Ilan.
With respect to those nano diamonds, I mean, you haven't shown, unless I missed it, any structural information. So what makes you so sure they're diamonds, actually, not some other form of color?
Oh, the other people did that. They're diamonds, yeah. No, they did that. The people we cooperated with who gave us the nano diamonds, they told us that they're nano diamonds. They studied them before. You know, they studied structure. There was no...
But in principle, you could do that using the field ion microscope. I mean, using the crystallographic capability of the...
That would be hard with the field ion microscope. The main reason these experiments work is because of the UV laser that allows us to dissect these dielectric materials. Okay? But they're nanodiamonds. They've studied this particular meteorite. A lot of groups have had access to these nanodiamonds, and it's what's left, I said. After you remove everything else in the meteorite, you have nanodiamonds and nanoparticles of silicon carbide, and we also looked at the silicon carbide particles. Okay? But no, they're diamonds.
My question was more methodical on the method. I mean,
You want to know whether they're amorphous or crystalline, or?
I want to know whether you, with this instrument, you have the capability to do that as well, to get a crystallographic information.
It's the wrong technique to get crystallographic information. Either you want to use X-rays or you want to use selected area diffraction in an electron microscope. Its strength is getting the chemistry, and that's why you have to use it in correlation with other techniques. I mean, it's in my group, students have stopped using the field ion microscope part, which does contain information, as you said. The reason is technical. Is you have to we have an ultra-high vacuum system. They have to bleed in helium to a pressure maybe with the channel plate, maybe you could get away with 10 to the minus 5 torr, 10 to the minus 6 torr, because we have high gain. Okay, you take your images, and then you have to pump out the helium, okay? And then you have to wait until you get back to 2 times 10 to the minus 11 torr. And they don't like doing that. We had another instrument which we built partially and we bought partially, and it had a maximum speed, a maximum pulse rate, and it was voltage pulsing of 1.5 kilohertz. And the record data set that we could get, one of my students, Chantal Sudbrock, who now works at NASA Glenn Research, she is an incredibly patient person, and over an 11-day period, which went over the Thanksgiving weekend, and she was lucky, she lived in Highland Park, which is north of Northwestern University. She collected 11 million atoms in 11 days. That figure sticks in my mind. And then we went up to Imago with some specimens of hers. It was then called Imago. And in one day, we collected more data in one afternoon with a prototype LEAP. It was an alpha version. We collected more data than she had collected in her entire PhD thesis. So once we had the LEAP in the laboratory, no student would touch it. Even though we had beautiful FI images from it, beautiful ones, they would not touch it, of course, because they could get these huge, it's human nature. They would get huge data sets in a few hours. In those few hours, it's like going to the synchrotron, where in a day or 2 days you collect a tremendous amount of data and then you spend a lot of time analyzing. It's the same thing here. You get a data set, say, with 500 million atoms, 250 million, even 6 million. I mean, you can spend a lot of time really squeezing that data set to get a lot of information. So it was very difficult to convince students to use the FIM part of the old version. It's human nature. If I was in their shoes, I would have done the same thing. Because you want.
If I made them the next question.
Yeah.
I mean, in that case, that combination with TM seems extremely powerful.
It is, yeah.
Can you elaborate a little bit how it's done technically? I mean, the
Okay.
procedure.
I can show you some slides. Okay. So. Here are these nanowires that were grown with aluminum as a catalyst, and they had a very high number density. You can see one over here, and then you isolate a few, so you deposit platinum. This is done ex situ, all of this. And then you isolate some like this in this region here, and then you see you want to analyze these 3, so you cut out material with the dual beam fib containing those 3, and you see that there are 3 down here, for example, and then there are more steps, and then you put it on a silicon micropost, and you sharpen it to a sharp tip such that it contains a single nanowire. These are the steps that are involved, and here you wind up with a single nanowire contained within this in this tip region. So. And then we can also, I have another example. You ask combining it with TEM. I don't have the one way. It's another transfer step. So you take a grid, a TEM grid, and it's one where they're numbered or lettered A, B, C, and then you can take a nanomanipulator and you can attach the nanowire to these pieces of copper on the grid, and then you can look, put in an electron microscope and then look at them. And then you can take one of those same specimens, and this is tedious, of that same specimen, and then put it onto a silicon micropost for the atom probe tomography. This is really tedious. I mean, that's tedious.
Sounds like there are a lot of skills.
Yeah, you need good dexterity, but the more you do it, the more often you do it, the better you get at it. Not me, but in particular, Dieter Isheim and Sung-Il Beck, they're very good at this combined technique in my group.
Very impressive.
I have nice images from the paper that we have not submitted yet that I can show you that describe stage by stage all of the process.
Yeah.
I mean, macroscopically, how it looks like. Any more questions? So if not, but please stay for a minute. I have one short, quick comment. So thanks, David, again for this wonderful talk. David and Bruce, Matthew sent an email regarding the airport. I've checked it. I have official